Hi Bob, I've been reviewing the quantum computing papers from December 2025, and there's so much happening across different fronts. I'm curious to hear your thoughts on what you see as the key developments this month.
Hey, Alice. Yes, December was quite eventful. I'd say one of the most exciting developments is the work by Rosenfeld and colleagues on magic state cultivation. They actually demonstrated this on a superconducting quantum processor, achieving a state fidelity of 0.9999 with only 8% of attempts retained. This is a major step toward practical, fault-tolerant quantum computing, because magic states are essential for universal quantum computation, yet they're incredibly resource-intensive to produce through traditional distillation.
That's impressive. So they're moving beyond distillation entirely? How does cultivation differ from the standard approach?
Great question. Traditional magic state distillation takes many noisy magic states and distills them into fewer, higher fidelity ones. It works, but it's extremely expensive in terms of both qubits and time. Cultivation, on the other hand, starts with a surface code and uses code switching techniques to directly prepare high-fidelity magic states. The Rosenfeld team reduced errors by a factor of 40 compared to the initial state. The key innovation is that they're not just filtering out bad states, they're actively cultivating good ones through the error correction process itself.
I see. And they mentioned this was tested on IBM Heron R2 processors. Does this mean the technique is ready for near-term deployment?
Well, it's a significant proof of concept, but there's still work to do. The 8% retention rate means you're discarding 92% of attempts, so you need many shots to get usable magic states. However, this is still far more efficient than traditional distillation at comparable fidelity levels. What's really promising is that this approach is compatible with existing surface code architectures, so it's not requiring entirely new hardware paradigms.
Speaking of error correction, I noticed Aharonov and colleagues introduced something called syndrome-aware logical error mitigation, or SALEM. How does this relate to what we just discussed?
SALEM is addressing a different but complementary problem. Even with error correction, you'll still have residual logical errors, especially in near-term systems where physical qubit numbers are limited. Traditional error mitigation techniques ignore the syndrome data from error correction, but SALEM leverages it. The key insight is that syndrome measurements give you information about what errors likely occurred, and you can use that to better mitigate the logical errors that slip through. They showed this can increase the size of reliably executable computations by orders of magnitude compared to just using error correction alone.
So it's like getting two benefits from one measurement, error correction and error mitigation simultaneously.
Exactly. And here's the really interesting part. They found that in certain regimes, SALEM can actually outperform physical error mitigation even above the fault tolerance threshold. This challenges the conventional wisdom that error correction is useless above threshold. The runtime overhead of SALEM is exponentially lower than previous logical error mitigation schemes, which makes it practical for real computations.
That's a fascinating connection between error correction and mitigation. Now, I also saw the Alpha Qubit 2 paper from Senior and the team. They're claiming near-optimal decoding for both surface and color codes. How does their approach differ from traditional decoders?
Alpha Qubit 2 is a neural network decoder, and what makes it special is that it achieves near-optimal logical error rates while being fast enough for real-time decoding. They demonstrated decoding faster than 1 microsecond per cycle, up to distance 11 on current hardware. For color codes, which are more resource-efficient than surface codes, but harder to decode, Alpha Qubit 2 is orders of magnitude faster than other high-accuracy decoders. The key is that they train the neural network on realistic noise models and measurement errors, not just idealized scenarios.
Why are color codes harder to decode? I thought they were just another type of topological code.
They are topological, but their structure is more complex. Surface codes have a relatively simple 2D lattice structure with well-understood decoding algorithms, like minimum weight perfect matching. Color codes have a more intricate geometry and require more sophisticated decoding strategies. The advantage of color codes is that they can implement certain logical gates transversely, which surface codes cannot, making them potentially more efficient for fault-tolerant computation. But this comes at the cost of harder decoding. Alpha Qubit 2 makes color codes more practical by solving the decoding bottleneck.
I'm starting to see how these pieces fit together. Better magic states, better error mitigation, and better decoding, all pushing toward practical fault tolerance. But what about the distributed computing side? I saw Chen and colleagues propose the Mod-N-Hub architecture for distributed quantum computing.
Yes, Mod-N-Hub is addressing a critical challenge. How do you scale beyond a single quantum processor? The idea is to network multiple quantum processing units through photonic interconnects. The key innovation is a hub-and-spoke architecture that centralizes entanglement generation and quantum memory. They showed through Monte Carlo simulations that with adaptive orchestration, they can maintain about 90% teleportation success rates across 1 to 128 QPUs, whereas naive sequential approaches degrade to about 30%.
So they're using teleportation to implement non-local gates between different QPUs? How does that work in practice?
Right. When you want to apply a 2-qubit gate between qubits on different QPUs, you can't just directly couple them. Instead, you create entanglement between the QPUs, typically bell pairs, and then use quantum teleportation to effectively implement the gate. The challenge is that generating these bell pairs takes time and has losses, especially over longer distances. Modern HUD optimizes this by maintaining a small cache of pre-generated entangled pairs and launching parallel entanglement generation attempts. The orchestrator schedules everything in real time to maximize throughput.
That makes sense. But they mentioned the cost is higher average entanglement attempts, about 10 to 12 versus 3 for the baseline. Is that a significant overhead?
It is an overhead, but it's a worthwhile trade-off. The baseline approach might use fewer attempts per gate, but it has much lower success rates overall, which means you'd need to retry entire computations more often. Modern Hub's approach is more robust. You're spending more resources upfront on entanglement generation, but you're getting much more reliable execution. And as they scale to more QPUs, the benefits become more pronounced because the orchestration prevents bottlenecks that would otherwise compound.
Interesting. Now, shifting gears a bit, I noticed several papers on quantum algorithms for specific applications. The work by De Leon and colleagues on portfolio optimization using VQE caught my eye. They're claiming to handle up to 38 assets, which seems quite large for current hardware.
Yes, that's impressive work. They're using a hardware-aware methodology that tailors the VQE workflow to both the problem structure and the specific quantum processor they're using, in this case IBM FES. The key innovations are twofold. First, they implement something called ISQUAR, which improves solution quality for quadratic unconstrained binary optimization problems. Second, they use a constrained VQE method that decomposes the optimization task, allowing them to handle problems with more variables than available qubits.
How's that decomposition work? I thought VQE required encoding all variables into the quantum state.
Normally, yes, but their constrained VQE approach breaks the problem into smaller subproblems that respect the constraints of the portfolio optimization problem. They solve each subproblem on the quantum computer and then combine the results classically. This is particularly effective for portfolio optimization because the constraints, like budget limits and diversification requirements, have natural structure that can be exploited. The result is that they only need 29 qubits for 12 assets compared to over 100 qubits for conventional approaches.
And they tested this on real hardware, achieving performance on par with classical methods? That's quite a milestone for quantum optimization.
Absolutely. What's particularly noteworthy is that they're not just matching classical performance, they're delivering a broader set of high-quality investment strategies. Classical optimizers tend to converge to a single solution, but the quantum approach naturally explores multiple good solutions due to the probabilistic nature of quantum measurements. For financial applications, having multiple viable strategies is valuable for risk management and diversification.
That's a nice practical advantage. I also saw Goldsmith and colleagues working on the traveling salesman problem with VQE. They claim to solve 12 location instances, which is also larger than typical quantum demonstrations.
Yes, their approach is quite clever. They use a penalty-free formulation, which avoids the issues that plague many quantum optimization approaches, where you have to carefully tune penalty terms. They also achieve O(n log n) qubit scaling instead of O(n squared, which is a significant improvement. For 12 locations, they only need 29 qubits. They tested multiple encoding strategies, factorial, non-factorial, and gray encoding, and found that the choice of encoding matters a lot for performance.
What's the advantage of gray encoding in this context?
Gray encoding minimizes the Hamming distance between adjacent integers, which means that small changes in the optimization landscape correspond to small changes in the quantum state. This can help the optimizer navigate the solution space more smoothly. However, they found that the best encoding depends on the specific problem instance and the noise characteristics of the hardware. The key takeaway is that there's no one-size-fits-all approach. You need to tailor the encoding to your problem and hardware.
Speaking of hardware, I noticed several papers on quantum hardware developments. The work by Crute and colleagues on enabling technologies for superconducting quantum computing seems like a comprehensive overview. What do you see as the key challenges they identify?
That paper is really a roadmap for the field. They identify several critical areas: handling and transmission of quantum information within cryogenic environments, developing better control electronics, improving qubit coherence and gate fidelities, and scaling up the number of qubits while maintaining quality. One key point they make is that we need advances not just in the qubits themselves, but in the entire ecosystem: cryogenics, control systems, readout electronics, and classical processing. It's a systems engineering challenge as much as a physics challenge.
That makes sense. I also saw Jones and colleagues demonstrated mid-circuit logic executed in the qubit layer itself without routing to classical electronics. That seems like it could address some of the latency issues.
Exactly. This is a really important development for silicon spin qubits. Traditionally, mid-circuit measurements require sending information to the classical layer, processing it, and sending feedback back to the quantum layer. This loop has to complete before qubits decohere, which is a major engineering challenge. Jones and colleagues showed that you can perform feed-forward operations directly in the quantum layer by leveraging a back-action-driven control technique. This is the first demonstration of mid-circuit measurements in silicon spin qubits, and it could drastically reduce the power budget and latency of future quantum computers.
So they're essentially doing classical processing in the quantum layer? How does that work?
It's not quite classical processing. It's more like using quantum operations to implement what would traditionally require classical logic. The key is that they're using the measurement back action itself as a control mechanism. When you measure a qubit, the measurement outcome affects the state of neighboring qubits through the measurement back action. By carefully engineering this back action, they can implement conditional operations without needing to route information to classical electronics. It's a clever way to exploit what's usually considered a source of error.
That's ingenious. Now, I also noticed several papers on quantum communication and cryptography. The work by Zhu and colleagues on quantum cryptographic conferencing achieved 331.5 kilometers of fiber, which is quite impressive.
Yes, that's a major achievement. Quantum cryptographic conferencing allows multiple users to establish secure keys simultaneously, which is essential for quantum networks. The challenge is that you need to measure or construct GHZ states shared among all users, and the probability of successful multi-user coincidence detection is very low. Zhu and colleagues eliminated the need for coincidence detection by constructing GHZ states by correlating detection events within the coherence time. This greatly enhances the success probability and allows them to surpass the multi-user repeaterless bound.
What's the multi-user repeaterless bound?
It's the fundamental limit on the key rate you can achieve in a quantum network without quantum repeaters, based on the channel losses and the number of users. For multi-user scenarios, this bound is quite restrictive because losses compound with each additional user. By surpassing this bound, Zhu and colleagues are demonstrating that their approach is scalable to metropolitan-scale quantum networks. They achieved secure key rates of 5.4 bits per second over 331.5 kilometers, which is a significant improvement over previous demonstrations that were limited to about 100 kilometers.
That's impressive progress. I also saw Yam and colleagues working on practical quantum teleportation with finite energy codebooks. How does their work differ from standard quantum teleportation?
Standard quantum teleportation assumes infinite energy states, which is obviously not realistic. Yam and colleagues analyze teleportation with finite-size codebooks, essentially a finite set of possible states that can be teleported. They derive modified no-cloning thresholds and analyze security under public channel attacks. What's particularly interesting is that they show the secure fidelity thresholds can drastically differ from conventional no-cloning values. This is important for practical microwave quantum communication, which is relevant for superconducting quantum computers.
Why is microwave quantum communication important for superconducting circuits?
Superconducting qubits naturally operate at microwave frequencies, so being able to communicate quantum information via microwaves allows for direct integration with the quantum processors. This is in contrast to optical quantum communication, which would require frequency conversion. Yam and colleagues show that even with feed-forward losses and noise, you can achieve high-fidelity teleportation by using an appropriate feed-forward gain. This makes microwave quantum teleportation practical for distributed quantum computing with superconducting circuits.
I see. Now shifting to quantum algorithms again, I noticed Howe and colleagues proposed tree VQA for reducing shot counts in variational quantum algorithms. How does this work?
Tree VQA is addressing a major practical problem. VQAs typically require many tasks, for example, computing energies at different molecular geometries. And each task requires many iterations, each with many circuit executions. The total shot count becomes prohibitively expensive. Tree VQA exploits the fact that related tasks have similar quantum executions. It uses a tree-based framework where tasks are executed jointly at first, and the execution branches only when the quantum states diverge. This can reduce shot counts by 25.9 times on average, and over 100 times for large-scale problems.
So it's like sharing computation across related tasks? That's a clever optimization.
Exactly, and the benefits grow with problem size and precision requirements. For applications like molecular dynamics or materials science, where you need to compute properties across a range of parameters, Tree VQA can make the difference between feasible and infeasible. It's implemented as a VQA wrapper, so it integrates easily with existing VQA workflows. This kind of algorithmic innovation is crucial for making quantum algorithms practical on near-term hardware.
Speaking of near-term hardware, I saw Joe and colleagues working on error mitigation for fault-tolerant quantum circuits. They're claiming to leverage soft information from QEC decoders. How does that work?
This is a really interesting idea. Most QEC decoders output a binary decision. Either an error occurred or it didn't. But internally, the decoder computes probabilities or confidence scores for different error hypotheses. This is the soft information. Joe and colleagues show that you can use this soft information for error mitigation without any additional measurements or runtime overhead. They developed 3 techniques: post-selection based on decoder confidence, probabilistic error cancellation weighted by error probabilities, and zero-noise extrapolation using the soft information to estimate the noise level.
They're claiming this can reduce logical error rates by more than 100 times while discarding fewer than 0.1% of shots? That seems almost too good to be true.
It's impressive, but it makes sense when you think about it. The decoder is already computing all this information. You're just not using it in traditional QEC. By leveraging it for error mitigation, you're getting additional value from the same measurements. They show that compared to previous approaches that combine QEC with error mitigation, they can achieve up to 87.4% space-time overhead savings. The key insight is that error mitigation and error correction shouldn't be treated as separate. They can be tightly integrated for better performance.
That's a powerful idea. Now, I also noticed several papers on quantum simulation. The work by Wang and colleagues on using VQE as a fragment solver for LASSEF seems interesting. Can you explain what LASSEF is?
LASSEF stands for Localized Active Space Self-Consistent Field. It's a method for quantum chemistry that breaks a large molecule into smaller fragments, solves each fragment separately, and then combines the results. The key assumption is that there's strong correlation within fragments, but weak correlation between fragments. Wang and colleagues propose using sample-based quantum diagonalization, a quantum algorithm, to solve the fragment problems. This allows them to tackle fragments that are too large for classical exact methods, while still keeping the overall problem tractable.
So it's a hybrid approach where quantum computers handle the hard parts and classical computers do the rest.
Exactly. They tested this on iron complexes and water molecules, achieving within 1 kilocalorie per mole agreement with full LASCF, which is chemical accuracy. What's particularly nice is that this approach is compatible with near-term quantum hardware because you're only solving small fragment problems on the quantum computer. The classical computer handles the self-consistent field iterations and the combination of fragment results. This is a good example of how to design quantum algorithms that play to the strengths of current hardware.
That makes sense. I also saw several papers on quantum machine learning. The work by Ruin and colleagues on XQAIs for visualizing quantum encoders seems useful. What problem are they solving?
Quantum neural networks require encoders to map classical data into quantum states, and choosing the right encoder is crucial for performance. But it's currently a trial and error process because it's hard to visualize what's happening in the quantum state. XQAIs provides a visualization tool that lets you compare classical data features with their encoded quantum states and examine how different classes are separated in the quantum representation. This helps QNN developers understand why some encoders work better than others and guides the selection process.
So it's like interpretability for quantum machine learning.
Yes, exactly. Domain experts used XQAIIs to derive two key practices for quantum encoder selection: pattern preservation and feature mapping. Pattern preservation means the encoder should maintain the structure of the classical data, and feature mapping means it should effectively separate different classes in the quantum representation. These seem obvious in hindsight, but having a tool to visualize and verify these properties is valuable. It's part of a broader trend toward making quantum machine learning more interpretable and less of a black box.
That's helpful. Now, I want to ask about some of the more theoretical work. The paper by Gurevich and colleagues on Ising formulation and the TSP discusses some non-trivial issues. What are the main points they're making?
They're examining the gap between the Ising model formulation of TSP and what a realistic salesman would actually do. The Ising formulation is important for quantum algorithms like QAOA and VQE, but there are subtleties in how you map the real problem to the Ising model. They discuss qubit efficiency, how many qubits you actually need, and introduce a novel approach called discrete quantum exhaustive search that uses mutually unbiased bases to enhance VQE. The key message is that the Ising formulation is a useful tool, but you need to be careful about the mapping and understand its limitations.
What are mutually unbiased bases, and why do they help?
Mutually unbiased bases are sets of quantum measurement bases where measuring in one basis gives you maximum uncertainty about the outcome in another basis. For VQE, this means you can explore the solution space more efficiently by measuring in different bases. The discrete quantum exhaustive search approach uses this to enhance the optimization landscape, making it easier for the classical optimizer to find the global minimum. It's a way to exploit quantum properties to improve classical optimization.
Interesting. I also noticed the paper by Sefer on exploiting reset operations to run circuits for free. That sounds concerning from a security perspective.
Yes, this is a novel security vulnerability. Cloud quantum computing providers typically charge per shot each execution of a quantum circuit. Sefer shows that by using mid-circuit reset operations, you can pack multiple circuits into a single shot and only pay for one execution. He demonstrates up to 900% reduction in per-shot costs on real IBM quantum hardware. This is obviously a problem for the business model of quantum cloud providers, but it also highlights the need to think carefully about how quantum resources are metered and charged.
How would you fix this? It seems like you can't just disable reset operations because they're needed for error correction.
Exactly. Sefer proposes that providers should charge based on the total number of operations or the circuit depth, not just the number of shots. Alternatively, they could charge for the total execution time. The key is to account for all the quantum resources being used, not just the final measurement. This is similar to how classical cloud providers charge for compute time, not just for the number of results returned. It's an important reminder that as quantum computing matures, we need to think about the economics and security of quantum cloud services.
That makes sense. Now, I want to wrap up by asking about the broader trends you see in this month's papers. What themes are emerging?
I see several key themes. First, there's a strong push toward practical fault tolerance. Papers on magic state cultivation, syndrome-aware error mitigation, and advanced decoders are all making error correction more efficient and practical. Second, there's increasing sophistication in quantum algorithms with better resource estimates, hybrid quantum classical approaches, and algorithm-specific optimizations. Third, we're seeing more work on distributed and networked quantum computing, recognizing that scaling will require connecting multiple processors. Fourth, there's growing attention to the practical aspects, security, economics, hardware constraints that will determine whether quantum computing succeeds commercially. And finally, there's a maturation of the field, with more rigorous analysis of complexity, resource requirements, and realistic performance under noise.
Those are great observations. It really does feel like the field is moving from proof-of-concept demonstrations to thinking about how to build practical, scalable systems. Thanks for the discussion, Bob. This has been really helpful for understanding the landscape.
My pleasure, Alice. It's an exciting time to be working in quantum computing. The progress in December 2025 shows that we're making real strides toward practical quantum advantage, even if there's still a lot of work ahead. Keep diving into these papers. There's a lot to learn.